Hello everyone. Welcome to the Stats for the Masses webinar. Today we're covering multiple imputation, righteous approach to handling missing data. My name is Elaine Eisenbeis. I'm the owner and principal statistician here at Omega Statistics. We've had a large number of registrants for this presentation. I see many re-attending with us, so thank you for taking the time to join us live. Most of us encounter missing data values in data sets, so let's just get into it and start talking about it. I very rarely see a data set that comes through that's complete and beautiful. Today we're going to present a rather simple example of multiple imputation. We're going to use SPSS software. Today's just an overview, but I hope that the information you receive today will give you some ideas and guidance on how to handle missing data in ways other than just deleting them, deleting records. I mean, you don't want to do that if you don't have to. But as I say in all of our webinars, you use what you learned today, you try to apply it in a holistic way to what you're doing. It's my hope that if nothing else, you're going to come away from today's presentation feeling a bit more in control of your capabilities as a researcher. Too often we're afraid of making adjustments to data because we're under the impression that if we make changes we're going to invalidate something. More often than not though, using the data as is without any regard to the structure of it, the missingness of it, or some of the requirements of the analysis you're performing, it's a lot worse. So you want to make sure that you make changes when they're necessary. I anticipate about 40 minutes of the presentation. That'll leave us about 20 minutes for some Q&A at the end. And I currently muted the line so only my voice can be heard. My assistant is here though, Heather Crutcher. She's monitoring the chat board, so feel free to type any questions you have on the chat board and Heather will choose some to ask me at the end of the presentation. If you have any technical issues, you can type it to Heather on the chat board. Hopefully we won't have any today. We're notorious for always having something, but I think today's going to go well. I often find, though, if you do have some technical issues that just logging out and back into the webinar clears up just about everything. So when in doubt, reboot. And let's go ahead and see what we have going on here today. About Omega Statistics. Before we begin, I'll take a few minutes to tell you about us and the Stats for the Masses webinars, newsletters, upcoming workshops. Statistics can be difficult, even for seasoned researchers. Often textbooks, classes, training programs, they make things a little more confusing. My goal with the Stats for the Masses series and for Omega Statistics as a company is to inform and educate about statistical concepts in a way that we can all understand. Sometimes that's not easy, but we always try to do our best here so that everyone can see the elegance and usefulness of statistics. I think it's just beautiful. Here's some things about us. We are a private practice consultancy. We're based here in Murrieta, California. We do medical and clinical research. We do all phases of clinical trials. We also help independent researchers with experimental design, epidemiology, journal article assistance. We help with exploratory design and predictive modeling. That's probably one of my most favorite things to do. Dissertation assistance. We help with methods and results chapters. Also very rewarding to help researchers meet that dissertation PhD goal. Survey design. We do projects of any size. We have helped individual researchers. We help large companies. We do government work. Basically, we have our hands in just about everything as a private practice consultancy. And I really enjoy that, and so does the staff. We learn something every day, so like you, we're always learning. Our motto is to provide elegant solutions effectively applied. So let's see what we have coming up. I was trying to think of some things today. What do we want to do for the rest of the year? And I thought regressions. Everybody is interested in regressions. I think that's probably one of the most beautiful statistical models there is. You can do predictions. You can see how much predictors are affecting outcomes. It's just beautiful. You get so much information out of a regression. So we're going to have Regression Palooza. We're going to be focusing on a few of the many, many types of regression models for the rest of this year. So we have September 17th. I'm going to start with correlational analysis. It's always nice to know about correlations before you jump into the regressions. It really helps you to understand the multiple regression. Not so useful for logistic regression. It's kind of another beast altogether, but we will be covering that in November. And then on this, December 17th, I'm going to do my best to tackle hierarchical linear models, a lot of social sciences, educational research. In fact, these are nested type of models, students in schools, things like that. So they're becoming more and more used. The software, as software gets better, all these things can be done more easily. So we'll cover that in December. So you can go to our website, which is right here. There's a webinar page you can go to for more information and to register. You can also contact Heather Crutcher, and here's her email, and here's her phone number, and she'll sign you up. Right now I need to post them on the page, so give me until probably later today, tomorrow morning before you go and look, but hopefully we'll get that up soon so you can go and register. Okay. Oh, also, when you go to the website, sign up for the mailing list. You can also ask Heather if you shoot her an email. She'll put you on the mailing list. That way you can keep in touch with us, know everything that we're doing. We're doing more things all the time. Okay, well, let's get busy. So let's see what we have here. What is multiple imputation? Good question. I always like to start out with a textbook definition and then kind of make it a little easier with our Stats for the Masses definition. So if you look at the textbook definition, actually Rubin, he's Donald Rubin, probably back in the 1970s. He's the one that kind of started talking about different types of missingness, missing completely at random, missing at random, missing not at random. They all sound the same in a way, but there are some little differences which we'll go over very briefly. But that kind of led into also the multiple imputation procedures, and he also was very good at initializing that. And you can see, I mean, it's 70s, 80s. I guess it's longer ago than I seem to think. I have a hard time believing the 1980s are like 30 years ago, but I guess they are. However, it's rather new, relatively speaking. But multiple imputation replaces each missing value with a set of plausible values that represent the uncertainty. And it goes on to tell you no matter which complete data analysis is used, the process of combining results from different data sets is essentially the same. The way I like to look at it is it's a process used to fill in the blanks of a data set so that you have a full and complete set of data that you can use for your analysis. Nice and easy. So basically, we're just going to look at the blanks and fill them in the best way we can. Here we are with the types of missing data. According to Donald Rubin, about 3 classifications. They're defined in the order of severity. You have something that's missing completely at random. We call it MCAR. The missingness is random. Nothing's affecting the reason it's missing. It just is. Maybe somebody forgot to answer a question, and maybe it's just missing. It could be any number of reasons. The thing is about missing data, you never really know. You might know sometimes, but for the most part, you don't really know the function behind why it's missing. So you kind of have to look at the relationships, patterns of it and such, and see if you can determine from that what might be the best definition of the 3 for your missingness. When it's missing at random, completely at random, there's not a relationship between how the data is missing, the pattern, and the data that we have, the observed data. So, and the data that we don't have, right? So you have some data, you don't have some data, but what's that pattern and what's that relationship? There's nothing to it, really. You don't see any patterns. So in practice, a data set with less than 5% missing data for each variable can be considered MCAR. Also, you can look at overall if the data set has 5% or less missing for all the data points. A lot of times you can consider that also MCAR. When you have MCAR data, a lot of researchers will just take out the incomplete records, and that's pretty legitimate most times if you have that less than 5%. But a lot of times you don't. A lot of times you are missing more than 5%. So then you want to know, is it missing at random or missing not at random? So missing at random, this says that the missingness may be due to a relationship between how the data is missing and the observed data, but we can't see it for sure. Okay, often the data is missing. It's due to a variable we haven't even included in our data. So the pattern of missingness has a relation to the observed data, but not to the missing data. Again, I know you're probably asking right now, how in the world do I know that? You don't. And that's the thing. A lot of statistics is guessing. A lot of statistics is making estimation. In fact, that's all it is. If we knew the truth, I always say this, if we knew the truth, you wouldn't need statistics. So we have missing data, so we're going to look at some patterns you'll see in a little bit. We'll look at some patterns and maybe try to make a good guess at what we're going to do as far as handling it. But you never know for sure. So if you think there's an exact test or some kind of procedure you can use to see if it's MCAR or MAR, you won't know. There's just not. Probably the worst one, the worst severity is missing not at random. And the missingness may be due to a relationship between how the data is missing and the observed data. Again, we can't see it for sure. We'll never know for sure because we don't have the missing values to check against the observed values. So we can't look at any kind of relationship between them because half of them are missing. So in theory, data that's missing not at random, it's a pattern of missingness that has a relationship to both the observed and the missing data. And again, as I've been saying, we never know for sure about the true nature of missing data. But we can make assumptions on how to treat data sets with missing data, and we can make adjustments to the data accordingly. So there's many ways of dealing with missing data. Some are even better than multiple imputation in some cases. Some not so great ways are just to delete records. There's a list-wise deletion, and that's just a nice fancy name for saying just take out all the records that have any missing data. So if you have a person in your data set or a case in your data set and it's missing any data on any of the variables, it goes out. You don't use it. You just delete it. And it's fine to use for the most part if you have less than 5% missing data across all the variables, and that's because that's your MCAR. And I said it's easy peasy. Yeah, you just take them out. However, when more data is missing, if you take out entire records, you're going to reduce your sample size, which also reduces the power, so you won't be able to see significance even if it's truly there. There also could be systematic bias in the data, and that's when you have the missing at random or missing not at random. Remember, we never really know. But if you have 5% or less missing, you can usually safely assume that it's at random, or at least treat it completely at random and treat it that way. SPSS has a nice little option where you can do pairwise deletion. And what that is it's kind of like list-wise deletion, except you're only going to delete your record from the analysis if it's missing data for that analysis. However, if you run another analysis and it has all the data, you keep it. So it only deletes it whenever it needs to be deleted. So it's like it's list-wise deletion sometimes. So basically it allows you, if you say you have an ANOVA, you might have all the information for that. You have the group membership and you have the outcomes. But you do a regression and there might be some variables where you don't have information for a particular record. SPS with the pairwise deletion will let you include the person for your ANOVA, but it will take that person out for the multiple regression. So that's a nice little option. We use that quite a bit whenever there's less than 5% missing. Again, you don't want to use it otherwise. So some other not so great ways, single imputation. And what that means is you replace your missing values on your variable with one specific value. Some types include mean substitution. I'm sure maybe in basic statistics classes you've covered that, where you will just replace all the missing values on a variable with the mean score. So everybody gets that, anything that's missing gets the same value replaced. And median substitution is the same thing as mean substitution, except medians you're more likely to use when you don't have that normal distribution, because means, of course, as you know, means and standard deviations are related to the normal bell-shaped distribution. Maybe you have something that's skewed, maybe you have something that's a Poisson distribution, something like that. You might want to use your median. Long ago, back when they had punch cards for computers and on census data, I don't know if they still do it with census data, but they used to. You had hot deck imputation and cold deck imputation. Hot deck just means you use the observed variables that are in the data set, and then you randomly select them to replace missing values on the variable. So you kind of look at what other people have on that variable and just randomly choose from them to replace the missing ones. Cold deck is kind of similar, except what you're doing is you're using values from an entirely different data set. So you're not using the exact data set you have, you're using a different one. Why use multiple imputation? Multiple imputation involves creating multiple predictions for each missing value. So instead of going in and just replacing everything with one value, it would allow you to take that data, and it accounts for the uncertainty, and it kind of makes the best guess. Sometimes it'll do it via regression model. Sometimes it'll do it via other means. It usually simulates it over and over. You get a few different imputations. You get a couple values. It pulls the data all together, and then you get that main value that will be in your pooled data. I mean, you'll see as we go through it. This isn't the case with single imputation because they only have that one value that's going across all the missing data. So when you use a single imputation, you get smaller standard errors because think about it, if you're replacing, say, 20% of your data, your missing data, with one number, with a mean value, that's going to bring everything in towards the mean. You're going to have everything stacking up on the mean. You're not going to have a lot of variability, right, because everything's basically heading towards like a constant value. So that's going to make your standard errors much smaller, which is also going to make your confidence intervals much smaller. So you're going to get type 1 errors. And a type 1 error, that's when you see significance that's not really there. And that's a very bad thing. You don't want to say you're seeing significant differences when there truly aren't because your standard errors are too small. And so multiple imputation gives you better estimates of your variance and your standard errors and such so that you can be more confident that you're really looking at significance if it is there. Are there other ways of dealing with missing data? Absolutely. Depending on the circumstances, they may even be better to use. I mean, list-wise deletion might be just fine to use. I mean, it's easy, you know, but you can check out some other things in your spare time. Maximum likelihood estimation, the expectation maximization algorithms. In many cases, these methods make better use of the actual data and the distributions they're coming from, and they usually work better than a multiple imputation when you have smaller data sets. If you have larger data sets, it appears that the multiple imputation often does better. However, in practice, the maximum likelihood estimation and the expectation maximization algorithms, they're computationally intensive. They use numerical methods instead of simulation often. Some softwares have great programs for them. So, of course, it's one of those things where as computers get better and better, software gets better and better. They're becoming pretty easy to use also. SAS and M+ are some big ones that you could use with those. However, multiple imputation, it's easy, it's effective, and many studies have shown similar results between all of them. So I like this one because it's nice, it's easy, it still allows your research to have rigor, and that's important. There's some steps. First, we're going to check the pattern of missingness as best you can, because remember, we never know for sure. But we'll take a look at it and we'll make a good estimate, you know. We're going to impute the data set according to the pattern of missingness. Then we're going to take all those imputed values and we're going to pool them together, basically take an average of all those, and then we're going to derive our parameter estimates or standard errors of the estimates. We're going to get that from the pooled data. So we'll go ahead and give it a try. We're going to go into SPSS. We do need to have access to the missing values add-on. So SPSS likes to charge for every little bit that you add, so you will need that if you're going to use this process in SPSS. But let's go ahead and open up a data set. Okay, so here we have, I think we have about 29 countries, and this is some data with obesity rates for 2009 through 2011. And that's in percentages. It's the percentages through 2009 through 2011 of people over 65. And then here's the health cost per capita per person for each year in each of the countries. As you can see, we have a lot of holes. We have a lot of holes over here on obesity. Not so many over here. But it does appear that we have holes in the data across the board. But we'll look for sure to see. So let me go ahead and get my little notes out on this so I can walk through it with you. First, we're going to check the pattern of missingness. Okay, so we're going to go up to Analyze. We're going to go down into Multiple Imputation. Going to click on Analyze Patterns. I want to look at all my variables. I don't want to look at country name. We don't care about that. That's an ID, right? So we'll just look at all of these, though. So I'm going to click them all, and I'm going to move them over. And we want this. We want to keep this. We want to keep the patterns. We want to look at the summary. This is fine. Just leave it as it is. The minimum percentage missing for variable to be displayed, they have 10%. That's large. I want to see everything that's missing. I want to set it to a very low number, so I'm going to say 0.01%. That way it'll include everything. And then I'm going to click OK. And let's see what we get. All right, here's some nice little pie charts. Kind of gives you an overview. This first pie chart here, it tells you how many variables have missing data. And here's incomplete. How many are incomplete? All of them are incomplete. So 100% are missing data on at least one datum, right? They're missing at least one value. The second one is how many cases are missing at least one value. So this is record by record. So we have 27 of the countries had incomplete data. 2 look like they're okay. They're complete. So almost all of them are missing. And then the values. So on the values one is how many data points all together are missing. So we have, 181, another 80, probably 261 data points altogether. So of that, 80 of them are missing, about 31%. Well, we can't do the MCAR because it's over 5%. So multiple imputation is probably the way to go. Here's your variable summary. It tells you here how many are missing out of 20, I think we had 29 records, I think it was. Yes, 29. And here you can tell because here's the missing and here's how many there are. Okay, so for the obesity rate in 2009, 20 values were missing and 9 countries had it. And here's your mean and the standard deviation. Your means and standard deviations are according to the values that we do have, right? The data that is there. You can't tell anything about the missing data, right? So on your raw data, these are all the values you have. Let's look down a little bit further here. Here's where you can start looking at some patterns. Okay. The red are where they're missing. The white are non-missing. What you want to do with this is kind of see if there's some kind of pattern to the data. Sometimes you might have a lot of red up here and a lot of red down here. That would be a pattern. If in this graph you have the red and white just scattered all over the place, you don't have a pattern. I can see, though, from here that we do have a pattern down here somewhat. It's obesity. The obesity variables are missing a lot of data, and that's what we saw. So this is showing it right here. So I would say maybe this is a systematic kind of error. It could be missing at random, missing not at random. Definitely we've ruled out completely at random. Over here, here's a pattern. And let's see what your pattern, oh, I should tell you here. They're listed from the variables with the least number of missing data to the variables with the highest number of missing data. So obesity rate of 2009 had the most missing. The health cost per capita in 2011 had the least number of data missing. And then when you look up here, this would be pattern 1, this very top row. And what pattern 1 always is when there's no missing data. Okay, I don't know if that happened in our data set. It might have, I think, for 2 records, right? So not much there. But when you go down here, here's the pattern of 18 were missing on the red colored variables. So 18 were missing these ones. Okay. You go down here and you look a little further. You can see right here. This one's the biggest one, has a value of 13. Pattern 13 was the most prevalent, and it shows about 25%. of the cases had this pattern. So let's see if we go back up. Let's move some things around here, go back up. Let's look at 13. 13 would be right here. So here's 12, here's 14, here's 13. Pattern 13 had missing data on the 2010, 2011, and 2009 obesity rates. So most of the cases had that kind of missingness, okay? If you look down here, remember number 1 always means there's none missing. It's way over here. So probably we're looking at missing at random, missing not at random. Okay, so that'll give us some idea of where we want to go next. So we know we don't want to delete anything, we want to impute. So let's go ahead and do that. That's step 2. First, before we do the imputation, it's always nice to set a seed. Multiple imputation uses methods of simulation like Monte Carlo methods. I want to say Markov chain, Markov chain Monte Carlo methods. We'll just call it MCMC, right? So it does a lot of that simulation. So it's nice to have a starting point where you start your simulation from. So you should set a seed. That way, if you come back later, need to rerun it again, for whatever reason, you can start with that same seed and you will get the exact same results. If you don't set your seed, every time you run it, you can get a different set of results. So we'll go into transform. Okay, and then we're going to go to random number generators, which is down here. We want to set an active generator. I'm going to set the Mersenne Twister. It's a pseudo random number generator. It's one of the better ones. It's from Japan. I'm pretty sure that the authors are from Japan, but it's a very good one. It's used quite a bit. And let's set a starting point. You could do it random, but why are you setting it if you're allowing it to be random? We came in here to fix it. So let's make a fixed value. You can use the default, and that's fine. Just make sure every time you come in and do this that it's the same if you're using the same data and want the same results. But sometimes you might run them quite a bit, and so you want to maybe keep track of them somehow. Today's the 13th of August, so maybe I'll just say, I'll put today's date. August 13th, 2014. That'll be my seed. So we'll go ahead and do that. I'm going to click OK. And nothing much happens. You just get a little thing in your output saying that it was set. Okay. Now let's do our imputation. This is so easy. It's almost scary. Just go into Analyze, go into Multiple Imputation, impute missing data values. Okay, so first we'll take our variables. We want to look at all of them just to be safe. Oops. Let me try that again. There we go. So put that in. 5 imputations is all you need. A lot of times people, they get really strange about that because that just doesn't seem like enough. Shouldn't we do thousands? But 5 is good. 3 to 10. Is usually the standard, and a lot of people will use 5. I want to go ahead and make a data set. So I'm going to make a data set for it, and I'm going to call it imputed data. Okay. Now I want to go to the method. Now, we have different ways we can look at this. You can go with a custom method, and it's fully conditional, which is your Monte Carlo methods. And this is suitable when you have the kind of the random, arbitrary, right? You'll use that. There's also monotone, and that's what you'll use whenever you have a pattern, which is probably what we would use in this case. We would check this. However, SPSS also allows you to do an automatic, and it lets SPSS do all the work for you. Let it figure it out, and it's pretty good. So let's go ahead and do that. However, if you did use the custom methods, you could even specify down here what you want. Do you want to use a linear regression to run the imputations, or do you want to use the mean matching? A lot of times regression works just fine, and it'll work really well with this data because it's all scale, continuous kind of data. So let's go ahead and click on automatic. Let's make it easy on ourselves today. You can always look this other information up another time. Let's go to constraints. First thing you want to do is click on scan data. And what it's going to do is SPS is going to go back and look at the data file. It's going to tell you here how much is missing. It's going to tell you the minimum and it's going to tell you the maximum for each of the variables. Okay, so what you want to do is take a look and make sure that these make sense. We know obesity rates and the age over 65 rates, those are percentages, so those should be between 0 and 100. So here we have, they all look good, all between 0 and 100. Your health costs per person, they can be anywhere from 0 to, theoretically infinity, so you just want to make sure there's no negative numbers there. That looks good. All right, if you want to, you can define some constraints on what it imputes, because sometimes if you let it go by itself, you'll get negative values when you shouldn't. You'll be over a certain boundary that's just impossible. Like say, I don't know, I'm thinking, well, percentages, for instance, you want them all to be between 0 and 100. You don't want something that's 105. You don't want something that's negative 12, right? BMI would be another thing. You don't, very rarely would you see a person with a BMI over 70 or 80. So you want to be careful with that. So what I'm going to do, and I'm going to change my role, and I'm just going to call them, I'm going to say to them, we're just going to do impute only. I'm going to just do this down the board. And then here I'm going to say the minimum 0, maximum 100. Rounding, I don't want to round it. I want to keep my decimal places, so we'll go ahead and do that. So here I'm just going to go and put this in, and this in, and just go down. Software's great. You just got to plug in your numbers. It can be dangerous too, because unless you know what you should be getting, you could get yourself in trouble. But trust me, I know what I'm doing. So let's go ahead and put this in here. Okay, now here we have health cost per capita, or per capita. So we will impute it. The minimum I want to be 0. I'll leave the maximum open. We'll just let that go. We'll leave it be whatever it needs to be. But I definitely don't want it to be negative. So I'll put the 0 in. Okay, so I did that. Here's maximum case draws, maximum parameter draws. You don't need to worry about that. Just leave it the way it is. Sometimes you might need to make adjustments to make it run, more or less, to make the algorithm run. But for right now, it should be fine the way it is. So let's go ahead and leave it like that. And let's go to output. I want the imputation model. I want to see the descriptive statistics, and I also want to have an iteration history just to keep it in a file. So if I ever need to go back and check it, I can. So I'm going to give it a name. Let's give it, I'll just call it iteration. Oops. Okay. All right, so let's look at it. You click OK. This isn't so bad. It's just saying intercept only because we didn't choose to use it as a prediction in the imputation. However, we did get our imputations. So sometimes these warnings are more trouble than anything else. More bark than bite. All right, so here we have the imputation method, fully conditional. They imputed on these variables. Looks like all of them were imputed. So they all had something missing. Okay. And here's the model. It used linear regression to do the imputation. For the different variables, there were some that were missing. Some of them were missing 2 values on this one, but it imputed 10. Because the reason it looks like, oh my gosh, we only had 2 missing, how come it put in 10? The reason is because we chose 5 imputations, right? So we chose 5 iterations. So 5 different imputated models. So 2 times 5 is 10. So you'll notice everything here multiplied by 5 is going to come out with the values. Then we have some descriptive statistics, and we just want to make sure that they kind of make sense to you. Here's your original data. There were 9 records for the obesity rate in 2009 that had data. Here was our mean. Here's our standard deviation, minimum, maximum. And here's our imputed. There are 5 different iterations of the imputation. Okay, and so here are all the means and standard deviations for each of the imputations, and then minimum and maximums, and they're all looking okay. They're all between 0 and 100. In fact, they're pretty low. And here also is after imputation. Here are the data sets completed So we have now 5 full data sets, and there are 29 records in each one. Here's the mean for each of the data sets. Here's the standard deviation for each of the data sets, the minimum, maximum. It's always kind of nice to look and see, well, you know, how are they? Here the mean's a little bit off, and it's 13, but when we imputed it, it brought it down a lot. And you'll find that happens quite a bit. Imputed values always seem to be smaller because it's running from the information that's there. So it looks okay, though. I mean, they're within the ranges they could be in. Let's look at maybe the age over 65 here again. You have the 14 here, very small here. However, complete sets, pretty close. Let's look down a little further, so you have them for everything. Let's look at some per capita. Let's look at 2011. So here's the original data. Here's some imputed data with just the imputed values, okay? There were only 2 things imputed, so I mean you get a mean from 2 values, right? But again, smaller. However, when you put them all together and you look at the complete data sets that have been imputed, they're up there again, pretty close. Okay, so you just want to kind of look at that and make sure. Okay, so let's look at the imputed. We have 3 files now. We have our working data that we started with. We also have the imputed data, and we have the iteration file. But let's go into our imputed data file and take a look at that. All right, this has the raw data, which is what we're looking at now, and it also has the 5 imputations. So here's a variable that's been thrown in, and it's called imputation. If you go down, here's imputation 1. These little yellow boxes are the values that have been imputed. Okay, so if you go up here to the top, Australia for 2009 didn't have an obesity rate. So in the first data, okay, there it is. It imputed that value. You can also go up here. Oops. See if I can get up here. There's a little box up here. Okay, you can click on this where it says original data. You can also go down to your first. You can go down to your second. And see, here's our second imputation set. And it tells you which imputation. So if we go up a little bit further here, here's Australia for the second imputation, got 3.36. And here are all the other records. And as you can see, everything is supposed to be a percentage. I don't see any negative numbers, so that's good. And you can go all the way down to, you know, the 5th. Oh, there we go. Let's go back up. There they are. Okay. So it kind of shows you the data sets. All right. Now we're going to use this imputed data, and we're going to run a model. Okay. We're going to run a regression. We'll run today. So let's go ahead and do that. That's step 3. We're going to run our analysis. So to do that, we're going to go Analyze. We're going to go into Regression. And see right here, the little snail shell looking thing, that means you're using the imputed data. Okay, some of these you can't, and it won't have the little snail shell thing. That's what I call it. I don't know what you can call it, whatever you want. Little wave, I don't know, but it's this little curly Q. So what that means is that you're going to be using your imputed data set, and which is what you want to do. Okay, so let's go ahead and click on that. I'm just going to look at 2011 today. So let's say we want our dependent variable to be the health cost per capita, and then we want obesity rate for 2011 and a percentage of people over 65 for 2011. So those will be our independent variables, and let's just go in and just choose some things. I like this, I like this. Why not these? Get my confidence intervals. Continue for that. I'll go into plots. I always like to look at the residual plots. So we always put the predicted here, and we put the residuals in the Y. I like to look at histograms, QQ plots. We'll choose those. I don't think we need anything else right now. We'll just keep it simple. Of course, you have all those other options. All right. Let's click OK. All right, so down here it's running a regression. I don't know if you can see it on your screen, but it looks like it ran. Let's go into our output and click on regression. Here we go. Okay, here's our original data. There's our means, standard deviations for all of them. You notice there's only 7 values. We would have no power at all if we only used the 7. So list-wise deletion definitely would have been a bad idea. Here's our imputed data, so 29 records for everything. Again, this is also a small sample size, but remember, it's just a demonstration. If you had a regression, you probably would want at least 60 for this kind of regression with 2 predictors, but we'll do it with these. But here's the 5 different models, and then here is the pooled data. The pooled data is what you're going to use to report. Okay, what the pooled data is it took these 5 different data sets and averaged them to come up with the value for the pooled data. So you can see here the health cost per capita. Here's about 3,000, and here's it's quite a bit more. Okay, obesity rate is lower here than here, and here it's about the same. Age over 65, about the same. So those look pretty good. Correlations. Your original data here. Right here you can see the obesity rate was pretty strongly correlated with the health cost per capita, which means as obesity rate goes up, so does the healthcare cost. This actually looks like it's going negative. Of course, that's not significant at all because it's very small. And this one here, actually, let's see, significance, this one right here, you have a negative correlation between obesity and age. So it looks like it's the percentage of people over 65 goes up, the percentage of people who are obese go down, or vice versa. They're just moving in opposite directions. But that is significant. Okay, that's in the original data. Let's look down at the pooled data. Okay, we're looking in here for our significance. Nothing much going on there. Okay, so our correlations are a little less. How do you say? They're just less. They're just not as they're not as closely correlated, right? They're just not as tight, and that often happens because you have a lot more data. It's been imputed, so it's supposed to give you more better estimate of your standard errors. Let's look at our model summary. This will tell us our R-squared. That's the percent of variance that those predictors are bringing onto the outcome. So it's how much, in your original data, the obesity and the percentage of people over 65 account for almost 30% of the error in that outcome for health care costs per capita. And then down here is all the different imputations. This one was not a very good looking model at all compared to the others, but the other ones are pretty good. As you can see, you don't see a pooled value there. And that's a glitch in SPSS. For some reason, they don't have the pooled data in the model summary. So you either have to do it by hand or find some other means. Supposedly, they're supposed to be working on that and fixing that. And you can see here, too, also for the ANOVA model, no pooled data. Okay, so basically, your original data wasn't significant for the model, but here, your first one was, this one, and this one. These are at the 0.05 level of significance, which is the standard. But let's look down at the coefficients. Here we have our pooled data. Okay, so here's our original data. Let's see what we have here. Here's our coefficients. Okay, and here's our significant. Nothing significant. Of course, there's only 7 records, so I wouldn't expect it to be no power. However, if you look down here at the pooled data, which is what we're going to be reporting and using, if you're at the 90% level of significance, like if you're rejecting at p less than 0.1, then this would be significant. And up here, of course, it's not. So if you're looking at the 0.05 level, at the 95% level of significance, there's still no significance. But if we were looking at it at the 90% level, then we could say, yes, obesity is significant for that outcome, for the health care cost per capita. In fact, then you would go back and go, okay, for every 1% increase in the obesity rate, the health care costs go up about $93, okay? And then your average is about $1,600 per person over all the countries. So that's pretty nice. Here's our residuals. I like to look at the residuals. Remember I was talking about the normal distribution and such. Here's our raw data. When you have a regression, you want to check your residuals, make sure there's a nice scatter, right? Or just make sure that there's, that they're kind of following a nice distribution. And here, there's a big hole. There's a big hole right there in the raw data. But if you impute, look at the imputation models, much better. See, the holes are all filled in. This one's a little skewed off. And the guy out there by themselves, but they look better. The holes are basically patched. That one looks nice. I like that one. And then your probability plots. As you can see, what do you have? 1, 2, 3, 4. There's our 7 data points in the raw data. Not much to look at there. But here they are, lined up really nice for all your 5 imputations. So that's very nice. Oh, and here's our scatter plots. Yeah, it's scattered. There's our 0. It doesn't look too bad. Here's our 0 there. Actually, that's not too bad. Of course, with only 7 data points, you can't really see a pattern anyway. But here, now you can see a better scatter because now we have 29 in there. So they all look pretty good. Okay. So remember, you want to use the pooled results. And I guess that's about it. I guess I ran a little bit over, but let's go back into our PowerPoint. And let's go to the next page, and here's some more references. I didn't get a chance to do the SAS or the Stata. However, here's some information here. There's some seminars that they had at the UCLA Institute for Research and Education. It's a great online resource. I mention it every single time. Go there, look, learn, annotated output. It's awesome. It's awesome. So here's multiple imputation in Stata, and here's some in SAS. Okay, so you can look those up. This is a nice, easy read. If you just want to get an overview, learn a little bit more, read it at your leisure, it's a very good place. It's a paper by Jeffrey Wayman. Check out our blog, Stats Chat, soon for more information. I'm planning on putting a forum on there, too, so we can talk back and forth. You guys can talk to each other, et cetera, et cetera. So here's some information for me if you want to get in touch with us, and you'll be getting a PDF handout, so you'll be getting this information and the data set so you can play with it. All right, so questions. Let me see if I can make Heather live and see if we have any questions. Okay, Heather, are you there?
I'm here.
Yay.
Can everybody hear me? Okay, I have people shaking their head in the room saying they can hear me.
Okay.
Yeah, I actually had a few questions. Jenny asked, she was looking at the imputed values that were produced, and they seemed really low to her compared to the data set. She was wondering, am I looking at this wrong, or...
No, they will look low. A lot of times in any kind of imputation procedure, you do when you have the simple imputation, just the one value, of course you're going to have them kind of bunch up at the mean. However, what the multiple imputation does is it takes the imputed values, but it takes it with the end result in mind, right? So it's going to adjust those imputed values. So you're going to get something that's close to the mean value you started with. So the imputed data sets might seem small, but your pooled data with the average of everything after the imputed values are in there with the original data, it should be closer. So let me see if we can go up here and look. Okay. For instance, this is probably not the best one. Let's see. But Jenny is right. Jenny's always right. Let's see. Trying to find one. As you can see, here's the imputed values. They're way lower. Okay, but here they come back up a little bit. Not quite to where I'd like to see it, but you got to also know that there are only 9 values in here. So the algorithms and such, and it uses the regression. We use the linear regression to figure this. It's going to take into account what it does know and what it doesn't know, right? So it's going to pull, we don't know. This is probably much closer to what the real mean value would be once you put everything in. So the algorithms take into account that missingness too, something we can't see. So oftentimes you'll get your imputed ones will be much smaller, but when you put them all together in your complete data, they tend to go back up a little bit more. On some of these, no, not true, but there were some. Here's one, age over 65. Here's our mean with the But so we had 24 records to begin with. So as you can see right here, it's almost a full set. So you're going to get a little bit closer here. So it's just a function of taking into account that missingness, and somehow I don't know the exact way it does it. I could find out, but of course it'd be very technical and very labor intensive and math intensive to show exactly. But if you have a lot of missing data going in, you're probably going to get some little stranger values on your imputed, but it should all come back together in your complete set with the pooled data.
Okay. I have another question. This one from Rebecca.
Okay.
She said, when the values are actually created, the imputed values, what information is it taking from? Is it taking from the data that is in the set already and taking means, or how is it actually working?
There's different algorithms for it. The one we use today, we used regression. So what we did was we took all the data that was in the data set and we threw it into regression models. And then that helped us to find what the values would be that were missing on the variable. So there are ways you can do it by hand with regression. I mean, that's the old school way where you would just run regression after regression after regression and just try to settle on the value. But the SPSS does it. But there are other ways to do it. If you go into R or some other programs where you can actually choose some other types of distributions, you can do it that way. That's where your expectation maximization algorithms and such come in handy, because you can use a lot of different distributions and figure them that way. So that's where they're kind of a benefit over the multiple imputation. But in this case, we used regression, and we took all the data we did have. It adjusts for the data we don't have, which is why you get those kind of freaky estimates on the pooled set, or not on the pooled set, I mean on the imputed set. But it all, like I said, it all comes back together on the pooled set. And it sounds like cheating. I got to admit, it seems like you only need to do 5 of these simulations, pull it all together, and we're going to actually get something better than we had if we had left it missing. Yes, actually you are. And it sounds like these numbers are just coming out of nowhere. However, we are taking into account the data that is there.
Okay. Yeah, because Rebecca's saying if you have data missing absolutely not at random, will this still work?
Yes. That's the nice thing about it. Because like I said, you can't tell what kind of missing data you have. The only assumption you can make about the missing data is if it's less than 5%, you're just assuming it's missing completely at random. It could be missing at random. It could be a very systematic problem, but it's not going to hurt you, because you're only going to get rid of a little bit of data if you do decide to just delete them. But multiple imputation will work for MCAR, MAR, and MNAR. Missing not at random works across the board.
Okay. So it's not good just to delete cases that are missing. It would be best to try to do imputation on the data.
Yeah, the rule of thumb is if you have less than 5% missing, you most likely are okay. Nothing's absolute in statistics, right, Heather?
Right, we know that.
So as soon as I say, oh yeah, all the time, you can always delete. Yeah. If there's 5%, delete, then somebody will prove me wrong. So for the most part, 5% or less missing aren't going to impact the data. It shouldn't, unless you have data, unless your variability is huge and data's all over the place. But for the most part, no. So yes, you could do deletion, just list-wise deletion, just pull those records out if you have 5% or less. However, if you have more than 5%, you can almost be guaranteed that there's something going on besides just randomness. And that's when the multiple imputation would be useful. You could use it, you could use multiple imputation if you're only missing 1 or 2 records, However, I don't know if people would want to go through all that trouble if you're going to get similar results.
Okay.
Of course, it's not that much trouble, as you saw. It's not that hard to do.
Yeah. Because if you were to just keep all the complete cases and delete all the rest, you're losing a lot of data.
You can be, and that's the thing. If you don't have many to begin with, say, like in this data set, we only had 29 records. The last thing I want to do is pull anybody out. Right. Unless I have to. And to tell you the truth, this data set, it won't impute if something's missing across the board. I had Brazil in this data set, had no data on any variable. It was useless. That had to come out. right? But as long as you have values on at least one variable for each record, you should be able to impute.
Okay. Now, why would we use so few imputations? Like we only had 5 imputations in this presentation in the data. We did 5. Why not 100 or 50 or you know?
You only need the literature shown, and Ruben demonstrated that anywhere from 3 to 10 is usually optimal. You could do more, however, you're just there's a formula. It's a pretty simple formula. I can't write it here. I need to get something so I can write on a board. But basically, you would you take a rate of missing information, you divide it by the number of imputations, you raise it to a negative power, and add it to 1. Okay, there's your math. It's hard to explain without showing it. However, your rate and the number of imputations, it doesn't really matter. You can go from 3 to 20 to 100, and you're going to get the same kind of precision. So there's no reason to do 100. You could easily do it with the software, though. If you wanted to put in 100 imputations, you could, but you're going to get very similar results as if you just did 5 and pulled them. The precision's that good.
Mm-hmm. Okay. Jenny was asking too, because she had asked, she was looking at how low the imputed values were, and if they turn out being so low, she was wondering, is there something else you would try instead? If the ranges are if they're just too out of the range, was there something else you would try instead of imputation?
Try to constrain it. Right now I constrain those percentages to 0 to 100. However, the obesity rates, I doubt any obesity rate in any country is over 50. You might want to constrain it a little further, right? Okay. So, you know, check your research, check your literature, check to see, you know, what's possible. You know, I kind of left it, you know, I left every probable outcome in there, but it might be that you need to constrain it a little more. But the big thing to do, Jenny, is don't pay so much attention to the imputed values, except for maybe in your math in that data set. You want to check your imputed data set to make sure that you don't have anything weird in there as far as your actual values. However, don't pay too much attention to the imputed data sets. Look at that pooled data set. Right, so the pooled data or the complete data after the imputation, right? That's what you want to look at. And if those are looking okay or not too far off, you should be all right. There might be other things you might want to try, but I would say just, you know, the big thing about doing the imputation is about getting the right standard error estimates, getting the right variances. It takes into account variance, and that's important. And in order to do that and get the right variance and take into account that variance that's in your data for what you eventually get, sometimes it needs to give you some little kind of like wonky numbers. But if you look at the complete data after and it looks legitimate, it's reasonable, keep it. The other option is, too, you could always run it on the raw data. Well, and you do. I mean, it shows you the raw data, right? Compare your raw data to your pooled data and see how different, what different you're getting in significance and your parameter estimates. You know, that's also something you could look at. However, like I said, in this case, here we go. Here are constants very, very low on the original data. I mean, it's saying there's a negative, and the constant's supposed to be your mean, right? So it's supposed to be your mean expenditure per capita. Well, that's, you know, that's probably not right. So right there, your raw data don't look good. Imputed data, much better. So sometimes your raw data will give you rotten things too, right? So you want to make sure that you, you know, you're giving your models enough power and you're being reasonable with your variability. That's the big thing. And we're about out of time. Do we have other questions?
Nope, those were the only ones.
Okay.
Yeah.
Okay.
Yeah.
All right. Well, I guess that's it for today. If you have any other questions, you know, let me know. Send me an email. Send Heather an email. Hopefully I'll get that forum up soon, which would be great. And we're going to send handouts and the data set, and you can play with this and, you know, probably come up with more questions. But it's just meant to be an overview. So hopefully it was informative. Hopefully it, you know, whets your appetite for more of this. I think it's a great nifty little thing to know. And I thank you, everybody, for joining us, and thank you, Heather.
Thank you.
And we will talk to everybody soon.